Our next presentation, the topic is the project is construction of 3 large-scale robots capable of constructing UHPC shale, repair of culvert, and automated MFL, magnetic flux leakage detection system. Anthony Abrahao from our ARC Center is going to present that. Anthony?
It's a pleasure to be here. So I am a roboticist. I work in the Applied Research Center, and we are collaborating with Professor Aziz Naimini Group and providing support, mechatronics and robotic support to his applications. I work with robotics applied to nuclear waste, so I'm helping handling most of the legacy waste from the weapon program from the Second World War, the Manhattan Project. And then we have a quite interesting project, and now we are extending our some technologies to help the civil group in applying their technologies. So the objective is, my objective in this partnership with Professor Aziz Naimini, the Civil Department, is to develop a series of robots for printing and automating the UHPC-based solution developed at HBC, UCT under mainly Professor Aziz groups. So we have been developing, this presentation provides an overview of some of the automation process developed at FIU in construction, providing only a few examples. We have other projects, but we're just going to focus on shortcut and 3D printing. So in terms of FIU robotics project in civil, we are tackling the 3 main points in construction is inspection. So we have tools for inspecting structures and characterize damages. We also, in construction, build new structures from scratch, and also repair existing one. And our efforts are deploying UHPC. It has a lot of potential. And so in this presentation, I will present ultra high performance concrete, shell automation construction, and automated structure repair using UHPC shortcut. The project started in January 2021. We have several students from civil department, students from mechanical, and students from electrical, and then we are automating the process. So the goal of the project is deliver functional prototypes. So not only build robots, but also take the robots from the lab and try to deploy in field trips. It's a challenging aspect, but our main goal is to make something useful. Also push the boundary automated construction. So we pursue not only the practical aspect of today's need, but also we investigated technology that might be available in 5 or 10 years. But as academic institution, is our obligation to push the boundary. In training future roboticists with civil engineer backgrounds, that we will need a new type of working force. So a mixed civil engineer with also automation ability. We use our projects. The project performed most of them by the civil students, and we just provide guidance and support, but they execute the task. And also support automating process developed by a structural group is our main focus. So in terms of autonomy, in terms of robotics, we have building robotic systems. So we have current technologies, teleoperation that you can see anywhere. So you have your robot controlled by an operator, and most of the sensings come from the perception of the operator, his eyes and his ears. But also we can do a little bit further, the current research, supervised autonomy, where you have the robot perform the operation, and you have augmented reality that support the operator. For example, in this case here, we are using virtual reality. In the case that augmented the operation, the operator senses. However, the operator is still under control, But my goal, especially that is my expertise and my research area, is fully autonomous systems that you send there, especially in constrained environments and dangerous, and the system perform the full repair, recognize the failure, uh, take a decision on how it needs to be fixed, and also apply the repair. However, robotics in construction has a lot of challenges. So the environments are very harsh. Usually they are unstructured. You have the generated sensors. Most of our sensors are opticals, and then the dust and noise and smoke and clutter and people around can sometimes make hard to perceive what's happening. And also, construction has heavy tooling and payload. And another issue is lack of skilled labor that can operate this sophisticated machine. So reduce labor, improve quality and safety is being a steward from robotics in all tasks. In terms of the UHPC shell automated construction, so we are creating a way for you to select the geometry and then we print a structure. But we have, instead of printing layer by layer, we want to print the whole shell, and in a way that we can compromise between 3D printing, but also shell form work and provide a better solution, a compromise solution than in the middle. 3D printing layer by layer has a lot of issues. The issues are the bonding between layers are not strong enough. It's hard to put reinforcement inside the structure. And also it's quite slow. Form work has the advantage that is cost effective and easy to implement. However, is a fixed structure. Every time you want to change geometry, you're going to have to do the work of preparing the form and or reuse the form. As you can see here, he's one of Professor Zizi Namini student. So we developed this wood structure just to prove the concepts, the proof of concept. Now we are at the point to start creating the real machine. And then you can see we are able to create the moving, the section printing, and be able to create the print. So we were able to create a 12 inches by 8 feet shell. And this is completely made of UHPC. Now, we have been working with speed and other parameters. And now we're focused on variable knowledge geometry in a way the operator can select what geometry he wants and then don't have to make a fixed nozzle. And also large structure. Not only you can see structure is quite sizable, but we want to go to the full scale bridge construction. Also, we are creating, we are automating column printing as well. So there has some issues with rebar automation, and we are addressing those issues, and also how to create this variable geometry that we can print. But we are quite close to create our first prototype for vertical printing in a way the user can select what type of column he want to print, press a button, and he's going to get a shell of HPC concrete. Another important aspect is automated structure repair using high performance concrete, ultra high performance concrete. So in terms of automated means that, as I mentioned before, you need to be able to assess the degradation. The machine has to take decision and repair, and not only repair, has to go back and check the quality of the work that has been done, and sometimes even do a post operator like surface preparation to make a little bit aesthetic. So we have investigating several 3D mapping sensors for characterization. So in a way that we can, and also we use machine learning to try to identify the level of degradation. As you can see here, we went to some degraded columns, and then we can actually have a digital twin, and that would guide the robot in how to repair. But also after the repair is done, it's going to also check the quality of the repair that was made. Also, we are using concrete degradation. We have several tools with LiDAR. Then LiDAR is very adequate to get geometries and then a topographic information of structure. So as you can see here, it's just a demonstration, the potential of a LiDAR. This is our autonomous robot driving in a Applied Research Center corridor, and you can even see the posters on the wall. And then you actually have a digital twins that allowed us to evaluate the concrete degradation. Also, we have applied this technology to several platforms, ground platforms, backpack, and also drone, because according to unmanned vehicles, according to this, we need several solutions to address issues in construction. Also, the shotcrete, we are automating the shotcrete process developed by Professor Zizi Namini group. One of the aspects that we have faced is the hose and the nozzle that they use is very cumbersome to put in a compact machine. Our idea is to make a compact machine that can not only go inside a culvert, but also can spray columns, and it's not gonna be a heavy equipment. So what we have developed an articulate arm, and we have also create in-house swivel joints where instead of using the hose, we can just have an arm that can perform effortlessly the operation. So the idea would be this is a conceptual design to create a compact shotcrete robot. The robot's going to be smart enough to repair not only culvert but also walls and columns as well. So it has a lot of degrees of freedom. And in this scenario, we have also concerns about the sensory that a robot require to do the quality assessment and the structure. So we have developed the robot in two sections. One is where the spray is, and also the robot always move backward in a way that the area where the sensor is always clean. There's where the LiDARs and the cameras and also the actuators are. So objective is to full autonomous repair and also make some quality assurance. So this is our test with the articulated arm. UHPC has a lot of peculiarities regarding the pumping, and then what we want to try to prove is we can pump the UHPC through the articulated arm and also articulate the joints and not get clogged. And us also after we finish, we have tested if we're able to clean and perform, and then we were successful. So we didn't apply the compressed air because our question is, can we deliver the shotcrete, the concrete to the nozzle? And then yes, you can. Now it's just a matter of incorporating the nozzle to it. So here's our prototype. Then we have our robot. So our robot, the hydraulic and controls. So the system, our ideal system is going to be totally hydraulic, similar to a construction equipment, but however compact. So we're going to use hydraulic motors for the wheels, and then also hydraulic cylinders to to perform all the degrees of freedom that we need to perform our work. So this is going to be a cost effective, but right now, at this point, we are looking for a cost-effective prototype. This is our ideal, this is our dream solution. But now, of course, we have to prove the mechanics of it. So instead of go to a full hydraulic, we are doing cost-effective prototype. We are doing some bench scale testing. As soon as we finish that, we're going to start doing some full-scale testing. Then after that process, with our cost-effective prototype, we're going to do some design optimization of the process, and then we're going to try pursue the full prototype. As you can see here, here's some prototypes that were built in the lab. So we try to make very cost-effective. The idea is prove the concept that I can get my platform and my sensors to move around, to analyze the failure and apply the UHPC concrete, repair, evaluate the quality of the repair. So we are building two platforms. One is a real wheeled one, the other one with tracks. And you can see the articulated arms. Right now, we have test teleoperated, so the operator perform all the tasks. But also, we have evaluate the sensors in another task. So in the near future, we're gonna start incorporating the mechanics with the sensory and try to go for full autonomous repair or semi-autonomous. Sometimes full autonomous means the platform find the defect, but semi-autonomous, for example, means that the platform goes, scan the surfaces, give to the operator where the critical areas, the operator select and say, please go and repair this area. The platform go back and repair. But also we alleviating the operational costs of the operator has to control the joystick and try to make the platform, especially with all the degrees of freedom there is. And then so it's going to be semi-autonomous. The person operating the machine doesn't have to have full knowledge of the robotics. Just click, I want to repair this defect, and that is the condition that I want. Click a button, the robot goes, do all the repair, and then it come back. So the operator doesn't have to be trained like a joystick game or something like that that would burden the operator with tasks. Sometimes controlling a system is so hard that it's better for you to get and do yourself than send a teleoperated robot. So we want to compromise with semi-autonomous. The platform has the skills to perform the task, but the operator decide what has to be done in the sequence. Thank you. And questions?
Thank you, Anthony. Great presentation. It's really mind-boggling what you have accomplished and what you are going for. So the way I understood it's not only application of strengthening or so you are developing means to first recognize the issues and then do that. Is that can you say again what kind of like software or I'm guessing the LiDAR you mentioned, what else is there to recognize the, let's say, the repair needs and then send the robot?
So we have a combination of LiDAR it give you very accurate data, but also we have 3D cameras. Those cameras use stereo vision. They are very good for close contact. Sometimes they're more precise than the LiDAR. So the way we are working right now, we use the LiDAR for long range measurement. As soon as we get there, we use the 3D camera to evaluate the surface integrity. So that is what we are using. So a combination of 3D cameras, and we have tested several of them. We have tested all the available in the market. Right now, we're trying to get more cameras. However, due to the silicon shortage, most of the advanced sensors are back order. But as soon as we get them, we're going to test and see how we can use. In terms of software, we try to use everything in-house developed because we not only need to identify the state, the degradation of the concrete or the failure, but also we need to get this data integrated with the robot itself, so we cannot use third-party softwares, especially price, because even though they can analyze the failure, the degradation, I need to be able to integrate with my robot to make part of the decision-making process.
Thank you very much. Thank you for that good explanation. And I'm just for audience also know that our civil and environmental engineering program department is really lucky to have our applied research center close to us and being able to produce such a advanced and valuable product. Really, thank you very much again, Anthony, and we enjoyed the presentation.
And also, I would like to thank you, Professor Aziz Namini, because he has the vision to not only create research projects using robotics, but also he want to use them in real conditions. So that is quite rare nowadays. Everybody's doing a lot of research in the laboratory, but a few robots are leaving the laboratory and do actually work in the field.
Thank you very much. Thank you.